Okay, so today we are going to talk about continuous and discrete graphs and how do we know the difference between the two. So first of all, what are they? A continuous graph is a graph that does not have any holes, gaps, or jumps. So a graph that does not have any holes, gaps, or jumps. So if we look at these two graphs given, if you look, this is where the graph starts, this is where this graph ends, and all the way throughout, I can kind of draw my pencil across the entire thing without having to jump or pick it up or any gaps, which makes it continuous. So another example here is where my graph starts, where it ends, and it does move up, down, and kind of all over the place, but all throughout, it is one continuous line. So one way I like to think of it, a word that would be kind of synonymous with continuous, it kind of has some alliteration here. Continuous graphs are always connected. So that's one way to think of it, always connected. So on the other end, we have something called discrete. A discrete graph is where each data point is separated. So a graph where each data point is separate. So as you can see here, this is not connected. If I were to start looking at this graph, here's my very first point, here's my end, and if I want to get to this next point, I have to pick up my pencil to reach it. I have to pick up my pencil again, 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 and again. So there are a bunch of holes, gaps, jumps, whichever language you like to use. We have them all throughout this graph, so it cannot be continuous, so it is discrete. And same with this one as well, a bunch of jumps or gaps. So one way I like to think of this, discrete graphs are always going to be dotted graphs. So again, some alliteration to help. Discrete is dotted, continuous is connected. So our first task of the day is to be able to identify the difference. So looking at these example problems, it's just asking us to identify continuous or discrete. So this first one, this is the beginning of my graph. This is where it ends, and I can trace along the entire thing. There is no place where I pick up my pencil. So it is continuous or connected. Here on this graph, I have a bunch of dots, right? So I have to keep picking up my pencil. There's a bunch of gaps, so that is discrete. Here, starting from left to right, this is where my graph begins, and along the whole way, it is connected, so continuous, right? So go ahead and try these three on your own. Pause the video really quickly and try and label these ones as continuous or discrete, and then check. Okay, so for this one, again, we start on the left-hand side, and what I see is I can trace this graph all the way through without picking up my pencil, so it is completely connected or continuous. Same concept here, from left to right, I can graph the entire thing without picking up the pencil. It is connected, so continuous. Now here you can see a bunch of dots, so in order to graph, I have to pick up my pencil all throughout, so it is discrete. Okay, so pretty simple to start discrete and continuous from a graph, and that's easy because it is a visual example. But now we have to figure out from problems whether it is discrete or continuous, so from words. Now, in order to help us with this concept, there are some key questions that we'll ask of the problem. The key question is, can I have half? So we're going to ask ourselves is, can I connect these concepts all the way through, or are there going to be gaps throughout, like a graph? Can I have half? So that's what I always start with, but what we mean by that is, can there be decimals or fraction versions of the number? Decimals or fractions. But can I have half is a good starting point. So can I have decimals or fractions? So if we think about the age of a person, so if I were to say my age right now, I'm 28, but if I want to be more specific, I'm not 28 on the day, I'm closer to 29 than I am 28. So I actually might be 28 and 2/3 of the way through. Think about when you were a kid, you wouldn't just say I'm 6, you would say I'm 6.5 years old, right? So we actually age continuously, right? We don't have just I'm 28 and I say 28 until I turn 29. I'm 28, 28 in 1 day, 28 in 2 days. So I have these little decimal increments, which means age is continuous. So the number of words in a newspaper. So counting the number of words. So let's say we see the sentence, the dog went on a run, right? Something really random, right? If we were to count the number of words, we would say 1, 2, 3, 4, 5, 6, right? 6 words. So we don't have half words. We either have a word or we don't, which means this would be called discrete because you can't have half of a word or a third of a word. It's either a word or it's not. So the next one, the amount of water in your bathtub. So really quickly, when we're talking about water in a tub, we would measure that probably in gallons, right? Tubs are pretty large, so we would talk about gallons. So as you're filling up a tub, the water is rising, and you might start off with half a gallon, 1 gallon, right? Maybe 1 1/3 gallons, right? You can have all those increments, those different measurements all throughout. You don't just start with an empty tub and all of a sudden magically 1 gallon appears. It has to hit every level on the way up, so every amount, so that makes it continuous, right? Can you have half a gallon of water in your tub? Absolutely. So what I want you to do is pause the video and try to work through those questions for the next 3. So you're going to do 4, 5, and 6. So pause the video and try and decide continuous or discrete. Okay, so first one, number of books you carry home. So let's say these are all the books in your bag right here. You might have math, you might have science, and you might have a lit book, right? You either have a book or you don't. So that would be discrete. Okay. The height of your classmates. So height ranges all over the place. So for example, I am 5 foot and half an inch. Okay. You might have a classmate that is 5 foot and 6 inches exactly. You might have a classmate who is 6 foot and 1/3 of an inch. So thinking of the question, can I have half of an inch or half of a foot? The answer is yes, which makes it continuous. The number of cans of soup in a grocery store. So if you think an aisle, you might have 1 can, 2 cans, 3, 4, 5, 6, 7, 8, however many. But there wouldn't be half of a can on a shelf. There might be bigger cans, right? Like a large bulk can, but that would still be considered 1 can. So number would be discrete. So we are going to leave these 3 for class as a refresher, so make sure you leave these blank, and let's go ahead and flip to the next side. So our last thing we're going to talk about is a function. What is a function and how does it relate to what we're talking about? So a function is a relation of x and y values. So we're talking about a graph, coordinates, right? That's what we're talking about here, x and y values, where x does not repeat. Now that's a very basic definition that I'm giving you. This is a very layman's term one. The formal definition is a relation where every input, remember inputs are x, has exactly 1 output. So remember, input is x, output is y. So this is the more formal definition. Every input has exactly 1 output, but in other words, x cannot repeat. Now, one thing we are going to see that we want to address now is function notation is written a little bit differently. Instead of x's and y's, we will always use, instead of y, the notation f of x. And what that is saying is the function, we're calling this a function based on the variable x because x is the variable. So for example, here it says y equals 7m plus 8. Function notation would say our function based on the variable m is 7m plus 8. So one thing to just note as we move forward, functions, instead of writing the letter y, we use the function based on this variable. So how do we tell if we have a function or not? It goes back to the definition, and we are going to look at the x values only, because that's all we care about. Because why? They can't repeat at all. So here are some examples of the different ways that we might see our variables noted. So first is just a basic coordinate notation, x, y. So this first example is a function, and the reason why, if I look at all the x's, do I see any that repeat or are used more than once? Nope, so it is a function. Now looking at this example and looking at my x coordinates, I look through and these are okay, but then all of a sudden I have another 5. And what do we notice about these 5s? This first one has an output of 7. The second one has an output of 18. And that goes against the definition. Every input has only one output. Well, here, 5 has 2 different ones. So in other words, 5 does repeat, which means it is not a function. So again, we don't care about the y values. Talking about functions, we only care about x's. So looking at this example, 1, 2, 4, 7, 12, no repetition. Each one has its own output. It is a function. Now, if I look at this table of values, I have 1, 2, 7, and then another 2. And if I look at these, they have different outputs. This one goes to 1, this one goes to 6. So it does not follow our definition. X repeats or has different outputs. Now, for the graph, I'm going to come back to this and talk about it with something called a vertical line test. So we're just going to look over this really quickly and look at something called a mapping diagram. Now here you see the words domain and range. That's just x and y. So again, we're only caring about the x values. But what a mapping diagram does is it uses arrows to point out where these values are going. Okay, so if you look, I have -1. It has one arrow going to 5. 0 has one arrow going to 3. 2 has one arrow going to 3. And 3 has one arrow. So again, we don't care about the y's. We don't care how many arrows go to whatever over here. We care about just the x's. And if I look, each x has one arrow, which means each x has one output. So again, same idea, x and y. So in this first one, we see that -2 goes to a -1. -2 also goes to 3. 0 goes to 3. 5 goes to 4. And again, we don't care about the y's. We only care about what's happening to the x's. And if I look, this x value right here has 2 separate outputs because that has 2 different arrows coming out. So because of this one right here, it is not a function. Now, going back to the graphs, we have something called a vertical line test. And what we're going to do, how we work this, is we draw vertical lines throughout the graph. And what we are looking for is how many times each line intersects the graph. If there's one intersection for each line, then it is a function. If there is more than one intersection, it is not a function. Okay, so I'm going to go back up to these examples here. So if I look along this graph, if I were to draw a bunch of vertical lines, you would see each vertical line intersects only once on this graph. So one intersection for each line means it is a function. Now, if I look here, my very first vertical line, how many intersections does it have? It has more than one, right? It has 2. So that means this x output or this input of x has 2 different outputs, so not a function. So pause the video here and try these 3 on your own under this vertical line section. Decide whether it is a or if it is a function or not. Okay, so for the first one, drawing our vertical lines, we can see that each one of these intersects only once. So yes, it is a function. Here, the same idea throughout. Each time it only intersects once. So yes, it is a function. However, here, my very first line, what I see is that it has two different outputs, so it is not a function. So we're going to go through a couple examples here. I'm going to kind of show you two examples, selecting yes and no, why, and then I'm going to have you try a couple on your own, and we'll save the rest for class. So for this first one, mapping diagram, I'm looking at the outputs. Okay, so where are my values going? And if I look, each one of these only has one output, so it is a function because each x has one arrow, and that's it. So one output. Looking at this table down here, I see my x's, that's all I care about. And if I look at my x's, I have a -2 going to a +10. I have a -2 going to a -10. So two different outputs, right? So it is not a function because x repeats. That's the basic way you can explain it. X just repeats, okay? So what I want you guys to do is go ahead and try this one, the ones I'm going to star, this one, and this one on your own really quickly. Go ahead and try those three. We'll check them, and then the rest will be for class. Okay, so looking at my vertical values here, my x's, -2, 3, 2, and 1, it is a function because x does not repeat, right? We can, for the y, use very basic language. X does not repeat. For this one right here, I'm looking at my x values. So x's, if I look, they're all different ones. So that means it is a function because x does not repeat. And then for my graph, now this one is going to be a little bit different because we use something called the vertical line test. So I'm going to draw through each part of the graph, and I see that it intersects only once. So I'm going to say, yes, it is a function. But the reason I'm going to say is because it passes the vertical line test from above. So passes vertical line test. Okay, now these three we're going to save for class. So that is it, and we will finish next day.